Good morning, everyone. My name is Antonio, and I will update the status of my thesis, starting from the point I presented last year, and with any new things we have done during this year in this work about flow control in turbulence, together with my supervisors Andrea and Stefano. So one big question is why we would like to study this problem, why we would like to control turbulence. There are many cases in the aerospace science where turbulent flows are present, and this is why we would like to control them. This is the most classical example. There is a lot of drag forces related to turbulence uh, in aerodynamic surfaces, as in this example. And if we were able to have some control over this would be very beneficial, even if we are able to reduce drag just by a bit. But there are many other cases where turbulent flows are present. For example, we have mixing. For example, inside a combustion chamber, if we can enhance mixing, we can have, for example, a more efficient combustion process. Or we have also the jet produced by an aircraft and the engine, which also has a strong impact on the aircraft. And we also have, for example, swirling jets. In this case, this is an animation of a swirling jet applied to the fuel being injected in the combustion chamber. How can we do flow control? We can start from something as simple as small changes and optimizations on the geometry, but we are going forward. We have first passive control, and we want to move into active control, which is of course more complex. It requires some power consumption. We need to design this complex system in which we need to implement a set of sensors and actuation system, but in the end, we expect to be able to get something more efficient. The first part would be the flow sensing problem, where we have to start from uh, implementing this set of sensors that can provide us information about the state of the turbulence at each instant of time. We cannot do it with the classical hot wire probes because these are intrusive measurements that will cause further disruption on the flow, and this is something we want to avoid. So we want to sense the velocity field from measurements from sensors in the wall. So there is no flow disruption. We can measure any quantity that is related to the turbulence and the structures being developed in the boundary layer that are somehow related with the information in the wall. For example, pressure probes, wall shear stress, even heat transfer through the wall could be parameters that we could use. And this is essentially a schematic of how it would work. I would like to go through some literature review to provide an overview of the steps we want to tackle in this thesis. Here we have some examples from the literature where this has been done, estimating the velocity fields at some wall parallel planes from wall measurements. Uh, we can find linear techniques and also techniques using machine learning as convolutional neural networks, fully convolutional networks, or generative adversarial networks that are the ones providing most promising results and the ones I am using in this thesis. And in particular, we are doing this estimation, but in 3D, going one step forward. So in just one step, we don't estimate a plane, we estimate a region in space in 3D. Then we would have to implement the control. For this, we expect to develop some of these methodologies that have already been implemented in flow control with artificial intelligence. For example, reinforcement learning or genetic programming are suitable options for this. And finally, well, this is a problem with a lot of parameters that have a lack of interpretability. So we need to move from this black box model to a gray box model where we have some physical parameters that we can interpret somehow. So finally, we will need to reduce the dimensionality of the problem to make some interpretation, and this would allow further to make applications for this, because if we train this and we work with a specific flow, with specific velocity, specific conditions, it would not be valid when we are trying to apply it in any other condition. Along my first year, I did a literature review on the topics that I will be using, and I am using along my thesis, especially about control theory, control applied for this purpose of flow control, and also about the problem of neural networks for flow sensing. And indeed, I not only did the literature review on this, I also worked on this in my first year. And I also got familiar with the experimental techniques that I expect to use along my thesis. And now I am in my second year. First, I closed this work on the flow sensing, but implementing also a physical interpretation of this. On the first year, I mainly focus on the neural network and the reconstruction performance, but this year I try to assess, for example, the types of structures present in the boundary layer, in the original one, and which of these structures we were reconstructing to have a better interpretation of what we are doing. And also this year I am working on an experiment with swirling jets. We are not implementing control on this experiment, but in future representations of this experiment and similar ones, we would include the control. And in the third and fourth year, I would start working on the control, as I mentioned. Hopefully, at the end of this second year, I will start working on control, first in open control, and then we would move to closed loop. As possible actuators, we are thinking of loudspeakers, pulsed jets, as those here we can see in the picture below, pulse jets that put some small jet on the nozzle, and also plasma actuators. And we are also thinking about different configurations, as a free jet, as the swirling jet that I am using in the experiment I will show you now, or a configuration representing a combustion chamber that could be instrumented in the wall with a set of sensors and actuators. I want to show you some results of what I have done. This is the generative adversarial network I designed for the flow sensing. It consists of a generator network and a discriminator that we use just for the training process, assisting the generator that generates our flow fields. And last year I showed you some results of this estimation. Now I want to show some results on these structures that we are generating. Essentially, we have obtained some conclusions about not just how the performance is depending on the distance, but also the types of structures. In the turbulent boundary layers, we have very important structures as sweeps and ejections, and we found that the quality of the reconstruction is clearly related to the footprint they have on the wall. And even if a structure is big and extends far from the wall, it can be accurately reconstructed if it is wall attached and has a strong footprint on our sensors. And this is the experiment with the swirling jets. Essentially, we are taking measurements with 3 cameras for the tomographic PIV and also with microphones. The idea is to establish a correlation between these two, so that in a practical application of this, just with the information from the microphones, we could get at least, not of course all the flow field, but some important characteristics of what we are having in our flow, some periodicities and these kind of things. This is a picture of the experiment running, where we can see the region illuminated by the laser just in front of the nozzle. Here we have an example of the flow being reconstructed by the PIB process. In this case, we have the span-wise velocity, where we can see how it is generating these swirls. And these are the swirler components that we design and are inserted inside the nozzle to provide this azimuthal component. And to conclude, I would like to mention some achievements as part of my dissemination of the work with the flow sensing problem. I presented it last year in these two conferences. And for this year, I didn't participate in any conference yet, but there are a few of them coming. So this work of the flow sensing problem now being closed with the physical interpretation of the results would be presented in ITI with a poster and with a conference proceeding, and in ETC with a presentation. And the experiments of the swirling jets would be presented in the Spanish conference of Spanish Fluid Mechanics Conference. Journal articles, I expect to submit this first work about flow sensing hopefully this week. And I also participated in different courses on different topics as PIV, machine learning, also on aeroacoustics, and I expect to do one more course about machine learning for fluid mechanics this summer. And this is all from my side. I want to acknowledge the funding for my thesis. Me personally, I am fully paid by the Ministry of Universities under the FPU program. And also my experiments are mainly funded by the European Research Council under this grant. And that's all. Thank you for your attention.